Previously, we're looking at Newton's third law of motion, and there is another law that we can look at according to Newton, and that's Newton's law of universal gravitation. I want you to start thinking back on issues of gravity. I want you to start thinking back on issues of why things fall. And that has to do with Newton's third law. Newton's third law actually states that each body in the universe exerts or attracts every other body. So each body in the universe attracts every other body in the universe. So let's say we got two balls in the universe. They attract each other, and they attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The equation that summarizes that statement is the equation F is equal to G multiplied by m1 m2 over r squared. What is this F? This F represents the force of attraction, and this force is equal to G, which is a constant, multiplied by m1, which is the mass of the first object, multiplied by m2, which is the mass of the second object, object 1, object 2, divided by the square of the distance between their centers. You can stay there. Look at it. Think about it. These formulas, or this is one of the formulas that is found at the back of every exam that you are going to write. If it is a paper 1 exam, you will find this formula there. The force is in newtons, the gravitational constant G. You will also find it at the back of your question paper. All right? It's equal to 6.67 times 10 to the power negative 11 Newton meter squared per kilogram squared. The mass should always be in kilograms, the second mass also in kilograms, and the distance between their centers, which we are calling R, should be in meters. So this is the equation that we need to play around with when we are talking about Newton's law of universal gravitation. Each body in the universe attracts every other body, okay, with a force that is directly proportional to the product of the masses, and inversely proportional to the square of their distances. Now, there are some important concepts that your exam guideline requires you to know and to think about. Concepts like weight. I told you in the video where I was talking about the different types of forces that weight is the gravitational force the Earth exerts on any object that is near its surface, right? And we calculate weights by mg. We have done that when we're looking at questions involving Newton's second law. And mass. What is mass? Mass is the amount of particles that you find in an object. All right? So mass and weight, as you can see, are two different quantities. What are the differences between mass and weight? Quickly, mass is measured in kgs, weight is measured in newtons, right? Mass is a scalar quantity. You must remember what a scalar quantity is. Weight is a vector quantity. It is very important for you, grade 12, to know the difference between a scalar and a vector. How about the aspect of weightlessness? The tendency of an object to seem weightless, like in space, like when an object is inside a lift and the lift is accelerating downwards at the same acceleration as gravitational acceleration, which we now know is 9.8 meters per second squared. That is a state that we can define as weightlessness. These very important concepts are highlighted in your exam guideline, and they are also part and parcel of our workbook that you can refer to, the Revolutionary Science Workbook 1, which was written by Norman Muvoti and Timothy Sibeko. Let's move on now to some questions quickly and find out what do exam questions ask us about. Here is one question that says that the mass of an astronaut on Earth is m. Mass of an astronaut on Earth is m at a height equal to twice the radius of the Earth. What will be the mass of an astronaut? So remember, mass, this is playing up a little. Remember, mass is the amount of substance within an object, right? What do you think the mass will be of the astronaut if that astronaut is now at a different place or at a different height that's twice the radius of the Earth? Will it be 1/4 m? Will it be 1.9 m? Will it be equal to m? Or is it 2m? Think about it. Does the amount of matter in a substance change when you change your position? Obviously, mass has to remain the same. So our answer for this question is C. The mass is equal to m. Let's look at another question here from 2019, November. So we are looking at Newton's laws. And this is Newton's law of universal gravitation. Okay, which by now, as I mentioned, we must be able to state it. Look, the gravitational acceleration on the surface of a planet of radius r is g. So now they are talking about gravitational acceleration. We know acceleration due to gravity on our planet is equal to 9.8 meters per second squared, right? Here they are saying on a planet of radius r is g, right? The gravitational acceleration at a height 2r above the surface of the same planet is... How do we come up with the value of g? Let's talk about that a little. You know the equation that we gave earlier on that says F is equal to g m m1 m2 over r squared, or distance squared between their centers. If we are going to consider F as the weight of an object, right? Which means in other cases, we know that F is equal to m times g. If we consider it as weight of an object, right? If we substitute that F with mg, your g, m1, m2 over r squared, what will happen? If we are going to have the small g remaining, one of the m's is going to cancel out. We remain with g is equal to m times G, big G, over R squared to give the gravitational acceleration. For example, if we multiply the gravitational acceleration and the mass of the Earth and divide it by the square of the radius of the Earth, we find that our value is going to be 9.8 meters per second squared. All right, that is where the value of G comes from. In this question, it is said that the R is now squared. Look at the relationship between R and G. What is it? It is an inverse square. So, if you are going to double the value of the radius, right? If you are going to double the value of the radius, what is going to happen to the value of G? So let's try it. It's if we double the R, right? It means that G will be equal to Gm over 2R, and this is squared. If I take out the R here, a quarter times Gm over 2, that 2 is already out, so it's R squared. This is the same as G, right? Initial G. Let's call this G1. The final G, therefore, is a quarter of the previous G. Do we have a quarter of the G? Yes, we do. Our answer there is B. So, it is very important to understand how these relate. A relationship between the force and mass is directly proportional. In other words, when you increase the mass by a certain factor, any of the masses by a certain factor, the force is increased by that exact factor. If you increase R by a certain factor, you have to square it. And we come up with a situation where we should always understand that it is an inverse squared, like what we did in this instance. So the gravitational acceleration on the surface of the planet R is G. The gravitational acceleration at a height 2R above the surface of the same planet is going to be 9/4G. Right? Why is that so? Because it's a quarter of that particular value. All right, let's move on. They like these questions in multiple choice examples. Here is another question. And this question is of a person who is standing in a lift. And there is a scale, right? And in this particular situation, a person is standing on a bathroom scale that is fixed to the floor of a lift as shown in the diagram. The reading of the scale is largest when the lift is moving. Have you been in a lift? When do you feel weightless? The aspects of weightlessness. When do you feel like you have gained weight? This should help us come to the answer of this question. Upward at constant speed? No, it must remain the same. It can't be this one. Downwards at constant speed? No, it can't be this one. But when it's moving upwards at an increased speed, there is going to be an increase in the measurement of the weight. You can also think about it in terms of the force W that is increasing because the object is now moving further up. So that's the answer for this particular question. Let's move on to further calculations that we can do. Here is question 2.2 that we can work out. What does 2.2 say? 2.2 says a 200 kg rock lies on the surface of a planet. 2.2, the acceleration due to the gravity on the surface is 6 meters per second. 2.2.1 of 2017 says, state the law of universal gravitation. Are we able to state it? Write it down. Think about it. It tells you that there is a force that's experienced, and this force, every single object or a body in the universe attracts every other body, okay, with a force. And this force is directly proportional to the product of the masses and inversely proportional to the square of the distance between their centers. So this formula, you should write it in words, and that is stating Newton's law of universal gravitation. Let us move on to 2.2. Right here you realize I just wrote out the formula, but you must write it in words, which is something that I think should be simple to do. Each body in the universe attracts every other body in the universe with a force that's directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers, which is that. 2.2.2 says calculate the mass of the planet if its radius is 700 kilometers. What is it that we are given? We are given a rock that's lying of a mass, let's call it mass 1, is equal to 200 kgs. Okay? And we are given the gravity is equal to 6,0 meters per second squared. And this question is asking us to find, we got a radius. R is equal to 700 kilometers. But our radius should always be in meters. So that should be 700 times 10 to the power of 3 meters. Your conversion must come naturally to you. You must know how to convert these, how to convert meters to kilometers, how to convert kilometers to meters. So, we are given small g. We want to find the mass of that particular planet. So what are we going to do? The equation that we know that uses small g is one that's derived from your formula table. You can even derive it from your calculations, which I presented, where we came out with g is equal to big G, small m, big M divided by r squared. What do we have? We have got 6 meters per second is equal to 6,67, which is the big G, times 10 to the power negative 11 newtons, kilograms per kilogram squared, times, right, the mass of that particular planet, which we don't know, over the radius, 700 times 10 to the power of 3. There you go. You can do that calculation. Pull out your calculator. I'll give you a second to pull out your calculator and carry out the calculation. Yes, here is my blue baby. What am I looking at? Cross multiply and then divide. So 6 times 700 times 10 to the power of 3, right? Divided by 6,67 multiplied by 10 to the power of negative 11. As I said, this constant, you find it at the back of every question paper, the constant that represents G. And that will give us the value of our M. So therefore, the mass will be, or I forgot to square this, don't forget to square that, so my answer might be incorrect here. Let's go back again. So that's 6 times 700 times 10 to the power of 3 all squared. Be familiar with your calculator, so do this together with me. All right? And then divided by 6,67 times 10 to the power of negative 11. There we go. Our final answer is in kgs. We can leave it in kg, which is the mass. Write out your final answer for M. I think 4,41. All right? Kilograms. Okay. Check this answer, please. Okay, let us move on. That will be the mass of that particular planet, if you consider the calculation that we have done here. Let's move on to the next part. The next part says, if you are going to look at May to June 2019, planet Y has a radius of 6 times 10 to the power 5. A 10 kg mass weighs 20 kg on the same surface of planet Y. Calculates the mass of planet Y. What do we know? We know the weight. We know the radius of that planet. We want to find the mass of that planet. Just like you did here, the very same story. Your G, in this case, will be 20. Oh, this is the force, sorry. So this one is a bit different. We are going to use 2.2. We'll use F is equal to G, M1, M2 over R squared. See the difference here? We're using the value of G. Right there we're using the value of F, which is the weight, 20. And 20 is in newtons, that's fine. Multiplied by 9 times, 6,67 times 10 to the power negative 11 times the mass of the object 20 times the mass of the planet divided by the distance, which is in meters, so I'm fine, 6 times 10 to the power 5 all squared. Now to find the value of m, I'm going to say 20 times 6 times 10 to the power of 5 all squared divided by 6,67 times 10 to the power negative 11 multiplied by 20. What do you think your mass will be in kilograms? Once again, pull out your calculator and do the calculation. Very important. All right? 20 multiplied by 6 times 10 to the power of 5 all squared, right? And then divided by 6,67 times 10 to the power of negative 11 times 20, which is the mass in kg. And my final answer there is 5.397, so which is 5.40 times 10 to the power of 21. All right? Just check this one for me quickly. I think the mass of that planet should be something bigger. Let's see. We are saying, we go back to this one, we are saying 6 times, I'm seeing something could have been wrong there, let me just correct it, times 10 to the power of 3 all squared okay, divided by, that was 6,67 times 10 to the power negative 11. Okay, I see where I think we made a small error there. It will be still 4,41 times 10 to the power of 22 kgs. See, I forgot to put negative 11 on the power 10 there. It's always good to go back and take a look at your work and confirm your answers. And they should make sense. This can make sense as the size of a planet, and this can make sense as also the mass of a planet. All right, let's move on to another question. The distance between the midpoint of two metal balls. So we are now talking about two metal balls. We can talk about planets using Newton's law of universal gravitation. We can talk about metal balls because we say every object, all right? We say that every single object in the universe, right, experiences a force. Every body in the universe will attract each other. Even balls, all right, have got an attraction to each other. The distance between two metal balls, P and Q, represented respectively of masses 65, that's P, 80, that's Q, 90 centimeters from each other shown in the diagram. The question says, calculate the gravitational force P exerts on Q. I think that's straightforward. We are trying to find the value of F. Let's put a clean slate there And let's run through with that question. Mind you, these questions and more are found in our study guide. So 7,21 says F is equal to G M1 M2 over R squared. What is my information? My information is that P has got a mass of 65 kgs, Q has a mass of 80 kgs, and R is equal to 90 centimeters. Immediately, when I see the length or the distance between their centers not being in meters, I must change it. 90 times 10 to the power negative 2, so that it can be in meters. Remember, they are 100 centimeters in a meter. So in order to get meters from centimeters, we divide by 100. So in my formula, F is equal to G multiplied by mass of P times mass of Q over the distance squared. So what do we have? 6,67 multiplied by 10 to the power negative 11 multiplied by 80 multiplied by 65 divided by 90 times 10 to the power negative 2 all squared. Try that on your own. What will be the force? Remember, the force is in newtons. The force is in newtons. Let's see if you come up with the answer there. All right, so it will be 6,67 times 10 to the power negative 11 multiplied by 80 and multiplied by 65. Okay? Which one do you think will attract the other? The one with the bigger mass or the one with the smaller mass? Obvious, the one with the bigger mass will attract the one with the smaller mass. So our attraction is going to be towards the right side. So let's finish up the calculation there. Divided by 90 times 10 to the power negative 2, which is changing it to meters, all squared. Our answer there is a force of 4,28 newtons to the right. Why? Because force is a vector quantity. Very interesting. All right. Give only the magnitude of the force Q exerts on P. Only the magnitude of the force that Q exerts on P. What do you think? Equal, but opposite, right? So they just want the magnitude. So the magnitude of the same force that Q exerts on P is the same force that P exerts on Q. 7.2.2. Our answer is 4,28 newtons. The answer is 4,28 newtons. Now Q is replaced by a ball that is half its original mass. Right? Distance between the balls is now doubled. Determine the new force. Do not use the same formula as in 7.2.1. So I'm not going to use the same formula to do the calculation. I'm not going to have these and substitute these. How am I going to do it precisely? 7.3, 2.3. I am going to simply say, okay, what is happening here is that for my F, right, half the original mass, all right, G is still the same, so there will be a half the original mass, okay? And that the distance between the balls is doubled. So the distance between the balls, how am I going to do it? 2 multiplied by R. So the distance has been doubled. I'm not going to double 90, all right? What is going to be my new F? It's going to be a half over 4 G M M, that's PQ over R squared. In other words, a half divided by 4 is going to be 1 over 8. Now 1 over 8 of what? 1 over 8 of the original answer. I hope you had not deleted that answer from your calculator. 1 over 8 of 4,28 dot dot times 10 to the power negative 17. So I'm going to say 1 over 8 that is 1/8 of the answer, which is equal to 5,35. Now that's my final answer, so I'll round it off to 2 decimal places, times 10 to the power of 8 newtons. And I have done that without using any of the values. Did you see how we just did that? Yes, well done. So that's Newton's law of universal gravitation. Anything too difficult? I don't see it. Ciao from Chiefs.